I'll discuss a little bit about the carbon capture, mostly from point sources and what's been done instead of going into the transition and stuff. But as most of you probably know, the carbon capture technologies, their development states, what's happening. So I'll just briefly mention these things. So there's two technologies for the, well, let's step back and look at this. So if we just look at New Mexico, we're producing around 50 million metric tons of CO2. Most of it comes from the power. It's rapidly changing, it's evolving, because as solar power is coming online, coal is decreasing, natural gas is coming online. So it's an evolving process right now and may rapidly change. One thing which is not changing is the CO2 emissions from the industrial sources. So that's going to stay. It's not increasing, decreasing, just staying stable. So technologies which are currently deployed, one of them is a amine-based technology, very mature, been practiced for 30 years. And the most advancements done in this technology is to reduce the energy consumption, reduce the corrosion caused by the amines, and so to make it more economical for deployment at this scale. What we are working on in the amine space is looking at the degradation of amines from like natural gas derived CO2 sources. So capturing CO2 from a natural gas derived, actually a ship. So on the ship, natural gas is driving the engine. So our collaborators are looking at capturing that CO2. We are looking at the degradation of amines and how to mitigate that degradation, and also developing a kind of an offtake from the ship. So as ship come to the port, the CO2 can be offtake and moved to a sequestration site. So yeah, it's a mature technology. The most of the things happening is how do we reduce the energy consumption there? There's new solvents been kind of researched and coming online. But as we look at this, we think if carbon capture has to stay for 30 years, there'll be opportunities to swap MEA with the new solvents to reduce the energy requirement for this process. So in future, the anticipated is the cost may go down. The second major carbon capture technology coming online is a membrane-based technology. Our MTR is actually leading that effort. They are currently developing pilot scale systems, which would be deployed in Wyoming to, I don't remember the scale what they are building at. So that also shows promising. Both of these technology nominally is going to cost very similar, but as these technologies mature and further develop, new solvents come online, it's expected the cost would go down. So another emerging area, as we heard what Secretary Kinderdine spoke earlier, is the hydrogen production. My team has looked into hydrogen production with carbon management, especially if this could be a sustainable route to produce hydrogen if we go into biomass. So using gasification of biomass and then in like pure enriched oxygen, and then separating hydrogen from the syngas, that could be a sustainable source for hydrogen production, and could be like a bridging between the green hydrogen. So this does require carbon sequestration. CO2 have to be separated and stored. Looking at the cost, I think this has already been discussed. The hydrogen with carbon management right now is the lowest pathway to produce hydrogen at scale, given that electrolyzers can be almost on the order of 5 to 10 times higher than the hydrogen with carbon from like biomass or from natural gas. So that it's so hydrogen with carbon management can help us transition into the green hydrogen, and in times when the renewable energy is not readily available to run the electrolyzers. So for that process to happen in an economical way, there's certain advanced technology advancements are required. We've been working on is the air separation to produce high purity oxygen. Currently, cryogenic is the industry standard technology. However, when we look at the distributed hydrogen production, and distributed oxygen production for gasification, cryogenic is not very efficient. The efficiency of cryogenic air separation goes down as the scale gets smaller. So we're looking at developing new membrane materials so we can efficiently and economically produce oxygen at small modular scale to then use for modular gasification. And why modular gasification seems interesting is because a large hydrogen production, gasification technology for large scale hydrogen production is very capital intensive. You're talking almost $1 billion to $2 billion for a large 500 to 600 megawatt system. Versus modular, it can be small scale, more manageable in terms of capital. And as technologies improve, it's easy to put new, more advanced technologies on modular scale than to kind of retrofit a larger system. And then we are also working on membranes on the other side for hydrogen CO2 separation, such that we can simultaneously achieve a high hydrogen recovery while capturing high % of CO2. For some of these advanced membranes, we can go all the way up to 95% hydrogen recovery while capturing almost 99% of the CO2 from the syngas. So a lot of opportunities in this space, and advanced materials. Can we deploy these materials which are not only performing better than current materials, but also are tolerant to the syngas and the impurities present in the syngas? So as Robert just mentioned about direct air capture, EIA estimates that we almost need almost 1 billion ton of direct air capture by 2050. Part of it comes from the removal of the legacy CO2 emission, but some of it also comes from the lack of doing 100% capture on point sources. Right now, everyone's geared towards 90 to 95% capture from point sources. Those 5% still would get emitted. So if we would like to go to 100% decarbonization, we have to implement direct air capture. So, and as a futuristic scenario, in 30, 40 years, when we don't have fossil fuels used for anything, we still need a carbon source. EIA estimates that around 350 million tons of air, direct air capture can be done to have that carbon source for synthetic fuel production. Hopefully by then, CO2 conversion would have advanced, or we have found a way to economically integrate the renewable energy for CO2 reduction, and we can make fuels and chemicals with the CO2 captured from air. So what my team and what my group is involved at LANL is developing advanced materials for direct air capture. Currently, amine-based systems are the more standard materials for DAC. The problem with these materials is the durability and the oxidative instability of these materials, and they degrade over time. So if DAC, which causes the cost of DAC to range almost $1,000 a ton, which is almost like 20 times higher than the cost of capture from point sources. So there needs to be a significant improvement in the materials for DAC. If you think about deploying DAC for 30, 40 years, currently there are no materials which can last that long. So we're looking at improving performance of these materials, at the same time also developing testbed capabilities so these new materials can be tested under more realistic process conditions, look at the impact of startup, shutdown, other climate factors like New Mexico is very dry. So certain materials which may work in East Coast would not work in New Mexico because we don't want to humidify all the gas, which is a very expensive process. So developing new materials as well as developing the processes, testbed capabilities to inform the deployers about designing their processes. One interesting thing comes with direct air capture is we have all the excess power, renewable energy, which get generated in this region. Can that excess generation be used for the direct air capture of CO2? So for example, the capture can happen at night, colder temperatures, where amine systems work better, and then regeneration during the daytime when we have excess solar available. So, and then leveraging all the sequestration opportunities we have in the region, direct air capture, like deploying direct air capture in the region could be very beneficial in terms of like growing an industry, workforce development, jobs, and everything. So there's interesting potential there. I guess that's all what I have. So look forward to your questions after other speakers have talked.